Good afternoon, everyone. I'd like to welcome you to our series of engineering seminars. And today's lecture will be given by Dr. Karol Seweryn, who is an associate professor at the Space Research Center, as well as the AGH University of Krakow. He received his PhD from the Warsaw University in the field of robotics. He is the author of 70 publications and a member of American Institute of Aeronautics and Astronautics, as well as IEEE. He was involved in projects focused on drill and sampling, in projects concerning space exploration, and his research is focused on the dynamics and control algorithms for space robotics, as well as development of excavators and sampling tools in the in-situ resource utilization activities on the moon. Karol, go ahead.
Thank you, Tomek, for a kind introduction. I'm wondering if it's better to speak in Polish or English, because do it in English. Okay, it's fine. Okay, so today I will present the, let's say, the outcome of the parabolic flight experiment done in lunar gravity at the end of the last year. So I think first I will talk a little bit about the device which we developed in the previous projects, and then later I will talk about this experiment in details. So as usually we are starting, let's say, the discussion about the outcomes of the project, having in mind the environment. And in that particular case, the environment is a lunar environment. So on this picture, you see few information about that environment. We have the vacuum there. We have the very, let's say, wide range of temperature. We have the gravity, of course, the lower gravity. We have the dust, and we have also what is specifically interesting for me, the quite different than on Earth soil. Here by color, I indicated which, let's say, part of this environment was validated in, let's say, different project. The green one is related to Digger project, where we developed the sampling device, which is in the middle of this picture. And let's say the red one is the environmental aspect which we validated during the parabolic flight campaign. Few words about the lunar environment. We know the details due to the Apollo program. So we know the morphology of the surface. We know the regolith, which is everywhere, that this regolith is quite abrasive and difficult for astronaut. We also know that, let's say, the locomotion of the astronaut, but also the devices is quite difficult due to this smaller gravity. But not only Apollo, we had in the past the Soviet mission Luna to the surface of the moon, and few recent Chang mission, and which some of them also deliver the real lunar regolith to the Earth. In sense of the, let's say, mineralogy, we have, let's say, three main areas. We have a so-called lunar highlands, lunar mare, and the poles. So in sense of, let's say, of the regolith and what is below the regolith, we have a quite few cores which was acquired by Apollo astronauts, and these cores, okay, I don't know. It's not on my screen. So, okay. These cores were acquired by the Apollo astronauts, and there are few main differences between these cores and the let's say the typical soil on Earth. The one is related to the temperature. The temperature is below 10 or 20 centimeter, the temperature is well stabilized. So as you see, in all cases, the temperature below surface is around 250 kelvins. And another issue is the density of the soil. It is very loose material, which means around 40% of the relative density, and let's say increase rapidly to have around 90% just below, means just 20-30 centimeter below the surface. You will later see that this density is quite, let's say, important parameter and not well defined. I hope soon, means in sense of few months, we will be able to hear more about this density issue during the defense of the Arkadiusz Tkacz, who I see is attending in this seminar. So I will not talk too much because Arkadiusz will explain us details, let's say, in a few months. But anyway, it is important to indicate that this regolith is, let's say, three types of grains might be found. So one is nanophase iron. It is due to the volcanic, or maybe not volcanic, but the asteroid impacts on the, let's say, on the lunar surface. There is a kind of rock fragments, quite typical, quite similar to the Earth. And what is not very typical is kind of agglutinates. Agglutinates is like ashes in terrestrial condition, means means that the particles which has a very high surface or large surface due to the porosity. So these particles especially create a number of difficulties for devices interacting with this regolith. Particle size distribution is also quite specific, means this is very wide distribution. It is let's say from the micrometers to nanometer to millimeters, and it is quite flat, which means that we have different particles on, let's say, every depth. This slide is not very relevant for this, let's say, for this presentation. As you saw on the first slide, electromagnetic issue was not analyzed during these two experiments. However, in future, I hope that we will have a chance to focus on that. First, the phenomena is very interesting. Second, I believe that the charged particles may have an impact both for, let's say, robotic exploration as well as human exploration. We have several, let's say, lunar regolith analog available on the market, let's say. And I think 15 years ago, when we started our activities, we developed also the Polish one, which we still using. It is called AGK 2010, and it is the, let's say, typical lunar regolith analog, good for geotechnics. So it is not good for chemistry, not good for, let's say, from the mineralogical point of view, but it is good due to the for the geotechnical activities. Okay, I just want to mention that this exploration of the moon is not only the, let's say, scientific activity, but it is also important from the business perspective, and let's say the extraction of the water is something which was proven as a business solution. So even a few days ago, we could observe, those of you who have had access to the ITT system at ESA may observe that there is a new ITT for the ISRO demo payload, including the, let's say, the kind of system to let's say, to deliver the oxygen, and the oxygen is an important element to have the water, and the water is needed actually to prepare the fuel. So fuel is a kind of a service which could be, let's say, be realized from the moon base in future. Okay, now few words about these devices, because before I will start to talk about the flight experiments, means the parabolic flight experiment, I would like to be sure that the audience more or less is familiar with what we developed in CBK. And we have the experience with the devices interacting with the regolith, starting from our experiment for Chumurov-Gerasimenko comet, which was led by Dr. Grigorchuk. Then later we developed a couple of other systems like a CRET or HOMIC. Finally, we contribute to development of the HP Cube on the NASA InSight mission. And based on this, actually, we got the contract for development of the, we call it rotary clamshell excavator, but it is in principle the sampling device. And at the first stage of this activity, we simply compare four different solutions. The one was developed, and it is called oscillation corer device. It was developed by AGH University of Science and Technology. The second was based on our previous experiment called PACMOON, and in the frame of this activity, we call it rotary hammering device. The second, was a bucket drum for continuous excavation, and the last one, and finally selected after the PDR, was rotary clamshell excavator. So what is the rotary clamshell excavator? It is in principle a kind of a device which are able to move this orange shovel by 180, more or less 180 degree, and collect the sample. So what was the main drivers for this development? We, let's say, based on the results from the PDR breadboarding phase, we wanted to work with AGK 2010 lunar regolith as a really highly cohesive and abrasive lunar regolith. We wanted to have a single degree of freedom, slow speed, in comparison to previous hammering operation devices. It is slow speed solution with high gear ratio to have small dust generation. We wanted to have operation with different angle of attack. Angle of attack is an angle between the, let's say, normal to the surface. We wanted to minimize the mass, volume, and force on the interface. We wanted to collect around, let's say, 200 grams of the regolith per one operation, and dig up to 30 centimeter depth. And this, if you remember from one of my first slides, at the level of 30 centimeter, we have the regolith with relative density around 90% or 95%. So this density is really important. But for this device, another, let's say, design driver was crucial. This is this footprint, means we wanted to have device that shovel is bigger than the cross section of the whole device. We wanted to have such a solution to have a possibility to dig into the highly cohesive regolith up to 30 centimeters. So it is a kind of a solution which we can create deeper and deeper, let's say, hole, and not do that with hundreds of, let's say, operation, but with tens of operation. From the mechatronic perspective, we wanted to work in vacuum, in high temperature and industrial environment. We wanted to have the redundancy of selected components based on FMEA analysis and ability to sense the regolith. And last but not least, we wanted to reach the TRL6 based on the ECSS norms. So this was the design drivers, and this is the solution. We really spent a lot of the time to find the topology, mechatronic chain, let's say, or the mechanism chain. So we have 3 stages of the mechanism. We have the first stage is a special Maxon motor, which we, let's say, which Maxon designed or adopted specifically for us. We have the, let's say, second and third stage of the mechanism. There is a meter gear and the worm gear. And we have, let's say, shovel axis supported by the angular bearings with the felt, let's say, felt sealing to prevent dust mitigation, especially dust mitigation toward the motor. Because other elements like, let's say, bearings and the worm gear was, let's say, prepared to work with the dust. So here you have a few pictures how this device looks like. So it is quite complicated shape. Most of the elements were made by titanium, especially shovel and the main beam. This main beam was really challenging for the company who manufacture this component. It is the single part component made of titanium, and there is a number of threads, which is small one, means that one 1.6 millimeter. So it was a real challenge. Another challenge was the electronics. If you see, the driver is also inside the device, and this driver was also designed and developed based on the ECSS standards. Inside on the axis, there is also end stops. So the operation of this device is from one end stop to the second. Of course, we have an access to the Hall sensor, but the Hall sensor on the rotor side, and we are using them, but just to control the motor, not to stop the device. Okay, a few words about testing before I will switch to the, let's say, topic of today. Before we went to parabolic flight, we do the test in dusty or dirty thermal vacuum chamber. So you can see the chamber here, and you may also see how the device is operating that chamber. So I was really happy with that test, because it is not easy to, let's say, to run the test in, no case, not very high vacuum, but in the vacuum and with the dust where the continuous outgassing appear. But at the end of the story, we were able to dig into the soil, and you will see later that we, let's say, we done this hundreds of times, and the mechanism is still working. So this was one particular test which was interesting. The second one was done on the University of Łódź. They have the manipulator arms. As you see, they prepared a very nice, let's say, place, secured the arms. And what we've done there, we just dig into the soil to get such a curve. And this curve allows us to define the performance. For example, we were able to see that we need 25 operation to dig up to the 30 centimeters. And during that time, we collect 7 kilograms of the record. This is a kind of performance curve. And depending on the angle of attack, of course, this performance is reduced, especially if you are digging, let's say, deeper and deeper. Okay, and this what we, let's say, analyzing this device and treating this device as a mining device, we establish a kind of mining performance of this device, like energy consumption per kilogram of the regolith or the, let's say, excavation rate. And these, let's say, parameters are available, and other researcher or companies may use it to, let's say, for further developments. For us, it was really important from the system point of view or from the engineering point of view. It was really important the mass of the device, because this is something usually always discussing with our prime contractors. And in that case, the mass of the device is 1.91 kilograms. So the device was lighter than, let's say, required by ESA. Okay. So this was the, let's say, digger project founded by ESA and finished actually in 2024, at the end of 2024. In the meantime, we got also the project from the National Science Center. I have a privilege to be a leader of that project. And what we, let's say, what we've done number of analyses, let's say, going to the direction to establish the architecture of the mine on the moon. So I will not talk about the details. This project was has scientific nature with one important aspect, which I will mention in a few moments. So I got this project, let's say, in 2022. It originally should be finished more or less at the end of 2025, but it was extended to 2026. In a few moments you will see why. Okay, but so this is just a context, and now I'm switching for the parabolic flight experiment. So as it is, let's say, visible even from that, let's say, slide, this parabolic flight experiment was founded by ESA and NCN, because actually it's working that way that, let's say, PI submitting the proposal, ESA gives the slot, but the funding must be secured by the PI. And I have lucky to have the NCN, let's say, NCN project, which, let's say, give me a chance to build the experiment. But okay, later you will see the details in conclusion or lesson learned. Anyway, this is the team which was with the people who, let's say, who was involved on the proposal stage and later, let's say, during development. So we have three institutions: CBK PAN, AGH University of Krakow, University of Warmia and Mazur, and Spacey Company. And in that project, we wanted to focus on the terrestrial, on the, let's say, on the moon gravity, because in all experiments which we done, in the digger project, we were in our lab, which means that gravity impact our device, but especially the gravity impacted the regolith. So for mechanical device, it is relatively easy to somehow reduce the gravity, but it is in principle impossible to reduce gravity or impact on the soil. So this is the main reason why ESA accepted, let's say, our experiment. So how looks the parabolic flight? Parabolic flight, let's say, looks relatively simple. In details, it is not so simple. So it is not just a parabola. This parabola is generated in the way to have, let's say, lunar gravity condition with respect to the floor of the aircraft, more or less for around 30 seconds. So one single parabola, we have 1 minute of preparation, around 25 seconds of the hypergravity where we shouldn't do almost anything or lie on the floor. Then we have the lunar gravity, which takes around 30 seconds when we should operate the experiments. This operation should be simple. And then again, we have the hypergravity of around 2G when the let's say airplane is coming back to let's say to the initial altitude. So as I said, between this parabola there is around around 1 minute 45 seconds for repeating or preparation the experiment for the next parabola, because during one single day, which takes more or less 3 hours, we have around 30 parabola. Between each 5, we have 5 minutes break, and in the middle, we have 8 minutes break. I remember personally this 8 minutes because our public relation person asked me to give an interview during that 8 minutes. So it still was not published, but I I was really unhappy. Means I at the beginning I did that it is a very good idea, but during the flight it was not so so perfect. Okay, so this is the accommodation in the flight. This is the Airbus A310. So this is the accommodation of the flight. If you see, there was a 9 experiment. I would say from CNES, from DLR, from UK, from Canada, and from Italy, if I remember well, and of course from the German. And most of them was, let's say, experiments related to medicine or to medical experiments with people as subjects of the experiment. 3 of them was related to the regolith. So especially for sure, 2 last was let's say done for regolith. I'm not fully sure if the 7 that one. Okay, so at least for sure 2 last experiments were done with regolith. As you see, the let's say the envelope of the airplane is provided here. At the end of the story, we were in a little bit different place, so it was, let's say, updated at the last moment that our experiment was done closer to the point number 6, but this actually doesn't change anything except the fact that we was closer to the media zone, and you will see what this means in the while. So this is the schedule, more or less, of the activity. It is important for, let's say, for future. If some of you are interested in experimenting in such a flight, it is important to more or less understand, let's say, the schedule. It is like a little bit more than 1 year activity. The proposal submission was in September 2024, acceptance in February. Then I need to confirm that I have a secured funding for this flight, not for the flight, but for the experiment development. Then a visit in Bordeaux. Then we design experiment, the part of the experiment which was not available at the proposal level, and delivering the documents. These documents are not so extensive as for the space conditions, but still there is a few documents with, let's say, 100 plus pages with description of the instrument, especially impact on the safety issue in the airplane. So the shipment was done at the beginning of the November. We traveled to Bordeaux for 2 weeks. 1 week is for preparation. Then there is an experiment, let's say, presentation, and there are 3 days of flights and 1 day for let's say return shipment. Okay, so you saw two slides before, let's say how the experiment area looks like on the paper. Here is the picture. So our experiment, okay, you may see here on the left side the CBK logo. So this is our experiment. Our experiment, as you will see in the moment, is composed of 2 racks. The one was developed by CBK. The second was developed by AGH. So this is that one. And you may see that all experiments are, let's say, are located in the cabin. On the opposite, let's say, side, we have this media zone, and this media zone is also the free flying zone. So the operators were able during one of the parabola to, let's say, to see how this low gravity impact their body. And on the bottom, on the back, you will see the places where the crew and also the operators is sitting during the takeoff and landing. Okay, so now a few words of the experiment. So as I said, we had 2 experiments. The first experiment is the CBK experiment, where we wanted to test, as I said, the operation of the sampling device in reduced gravity. So the RCE, which is presented here on the right-hand side, is a just small part of this element. So it is inside this drum, which I also called washing machine, because in fact it is more or less the size of the washing machine, and there is a drum inside. This drum is an important element because this drum is used to move the regolith in the bin, and this regolith is moved to the opposite direction to reset this regolith. As I said, we have a chance to realize 30 parabola, and at least at the beginning, we had hope to perform 30 experiments. So during the development, we find out that we are not able to do, let's say, each parabola 1 experiment due to the time needed to reset the parameters. But at the end of the story, we had a plan to do more or less 24 experiments per 1 day. Okay, so we have the drum to rotate the device. We have the second actuator to swap the piston with the RCE. What does it mean? We need to close the bin each time the RCE is not digging. The simple reason is to not lose the regolith, especially if the bin is on the opposite side to the gravity. So we need to close the bin and also set the relative density. So by setting this piston, we were able to set the relative gravity. As you remember, this relative gravity is a really important parameter for the excavation. As I said, we have a container with the regolith, and 3 different regolith were tested. The third actuator is, let's say, actuator to switch the RCE and the piston. So you will see later on the movie that we are able in the, let's say, one position of the drum to change the piston with the RCE and to start the. On one side, we have also the camera to observe the regolith motion, because one of the wall of the regolith beam is a glass wall. And we have the inertial measurement units to record acceleration profile during the flight. Whole the system is in, let's say, big casing with the power supply, with the laptop, etc. Okay, this is, let's say, the PETER Part 1. The PETER Part 2 was developed by AGH University of Technology, and generally there were inside two experiments. One is an experiment to measure the, let's say, soil shear parameters. So there is a blade which is, let's say, moving the regolith, and this movement is recorded by the camera on this side. And the second experiment is the drum to measure the angle of repose of the regolith. This is the drum which continuously rotates, and the regolith slope more or less is setting on some angle, and this angle is used in the geotechnical, let's say, the geotechnical analysis. So we have two cameras and also control panels and electronics, and there was an additional sensor, MEXEN. Maybe some of you know this MEXEN sensor from the our astronaut experiment on the ISS. Ignis experiment. So this is the same sensor which one of the students wanted to use, and this experiment was also done. Okay, so here you may see few pictures, and I will look on the not be too long. Okay, so what you see on this picture, on the top left, you see the, let's say, our team. On the another picture, you see the two of operators during the flight. On bottom left, you see me with another operator on the third day of the flight, and let's say on the fourth picture, you see another experiment. As I said, most of the experiment was this medical experiment, and that special one was quite special one, which you see here. It was related to the fact that human body is really, for human brain, actually is very difficult to walk. Means not to walk, but to prevent. Yeah, I don't forgot the English name. So to prevent falling down to the surface. So, okay, in the lunar gravity. So they artificially create such a conditions and measure the response of the human body. Okay, now is the movie. I will try to talk during that movie. So you see our first entrance, our experiment is transported, and let's say we will work on this, hold the team before the experiment. Okay, the spacecraft, and the day before the flight, the first team, Konrad Rutkowski and Adam Kolusz. So now the first flight is, let's say, on air, and they will do the experiment during the flight. Okay, this is the third day where I was an operator, and my colleague was a second operator. I operated the CBK experiment. My colleague operated AGH experiment. Maybe now I can talk a little bit more. That in blue, let's say, suits, we have the operators. In orange, there is staff from Nova Space. This staff helping operators if they have the, let's say, healthy problems. during the flight, there was an accident in the first day. The flight returned from the Mediterranean Sea because not only one of the operators has an issue, not only with the stomach, but also he has a, let's say, panic attack. And there is a doctor on, let's say, on flight, but they decided to come back and they switch the operator for the new one and go to the air one more time. So this was actually the flight where the Konrad Rutkowski was on board. So we didn't know. We were on the airport and waiting for their return, and we just laughing that maybe something happened with our experiment, and maybe this drum is rolling in the aircraft. So okay, in the meantime, what you can see that people are preparing for the flight. So during the, let's say, hypergravity, we need to stay in place and doesn't move, because the moving, especially moving of the head during the hypergravity, is difficult for operators. So some of the operator is lying on the floor. Maybe you've seen, now we have the hypergravity. So we are somehow squeezed, and after 30 seconds we will be relaxed, and the body will see that the body will relax, and we need to keep ourselves to stay and let's say at the position and somehow operate the device. So you see on my screen that we have the steps, let's say, in the application, and we need to just click the steps. So it was still quite, let's say, demanding, but from the operator perspective, but let's say it was done this was the best what we can achieve in such a short time of the development. And then we have again the hypergravity, where we are trying to not move. And after the hypergravity, we have 1.5 minutes to prepare the experiment. So after the hypergravity, I'm starting the, let's say, clicking and selecting the following steps. Actually, my colleagues had an issue with the experiment, something went wrong, so he needs to restart the device. We have a GoPro camera. This was the doctor who, let's say, walk around. Maybe I didn't mention about this, but we got a injection of the scopolamine before the flight. And this is our experiment. So now you can see how the experiment will work. So every time, every parabola we needed to reverse the orientation of the beam, vibrate the device, vibrate the regolith to reset, let's say, regolith after each sampling operation. Then the container move back to the, let's say, to the initial position. Then the piston was moved down to set the density of the regolith. This also is done with the vibration. I think switch off the sounds, but yeah, then this piston is going up, and the RCE is moved to the position where we could do the sampling operation. As you see, there is a lot of cables inside, and there is a lot of electronics inside, because we wanted to have everything inside the drum. Okay, I will mention about this during the lesson there slide. Okay, now we have the sampling. So the RC sampling. This is from the camera inside the drum. We are sampling in the low gravity condition, and you will see that this low gravity really has an issue or impact after the sampling. The sampling takes around 20 seconds. And after the sampling, you may see that the regolith go down due to the change of the gravity condition. So this is the impact of the, let's say, of the gravity condition. Now the RCE will go up, and after that, after this operation, we come back to the initial state. So altogether, this operation takes 2 parabola. So we were not able to, let's say, to optimize the timing of particular sequence to fit with this 1.5 minutes before between the parabolas. Okay, of course, every time we need to give back the regolith because we cannot add the regolith after the, let's say, after sampling operation. And at the end of the story, we need to replace the RCE with the piston to secure, let's say, to secure the pin in the container, to secure the regolith in the container. Okay. If there is something else. Yeah, there is. There is very important part is there are few, let's say, pictures, but I mentioned about this that there is this media zone, and Konrad, I hope you are, let's say, you can say later a few words about these effects, because I didn't attend in this, let's say, area, but Konrad was really enjoying, as you see, the free flying zone. So the body was really low mass. And after, let's say, after this time, there is a hypergravity, and then after that, there is a lunch in the cafeteria. Okay, so this is the movie. After the movie, I wanted to mention few, let's say, lessons learned. Few first are related to the RCE development, so maybe not so important for this, let's say, seminar. I'm not sure, Tomek, I should finish more or less in few minutes. Okay, so I just want to say that few important elements that we reached 30 centimeter depth during the testing in the, let's say, in the laboratory condition. And also we survived the, let's say, the live tests. We've done almost 300 tests. The live, that this number was defined based on the FMEA analysis. And which is also important, we performed a test in different relative density in the lab condition and then later during the parabolic flight. We have an issue with the sample sensor. We built finally this sensor together with the Warsaw University of Technology. It is based on the radio frequency technology. But the TRL level need to be increased, and this is what we plan for the short future. Regarding the parabolic flight campaign, this is difficult due to many reasons, but one of them is the funding issue. We were really lucky due to fact that, okay, we got this project from GISA, so we didn't need to pay for the flight, but we need to have the, let's say, the funding for experiments. So we need to build the experiment. Fortunately, we had the NCN project and also, let's say, both, actually all partners, means the CBK PAN support us with the funding for traveling. AGH got some funds also for travels and a little bit for materials, and UWM also got the funding for the travel. But it is not typical thing, means we were lucky, but in the normal situation, when you're submitting the proposal, you might not have let's say, second project with the secured funding for such an activity. Okay, so this is an issue, and in principle, what I would recommend to somehow discuss this issue with Polish Space Agency, or at the end of the story, the delegate from the Ministry of the Science and Education accept our proposal, so he knows about our proposal. So there should be kind of the path to get the funding for the experiment. Okay, as I said, this lack of funds creates the difficulty in the CBK PAN. This might create the difficulties because there is no, let's say, no team to build the device. Let's say in our case, we were lucky because we were RCE developed in the previous project, so we had the, let's say, the device. We have, let's say, mechanical engineer who were with us in the, let's say, 3 months during let's say, during preparation of this project. But the electronics and software, this is something which was done by a PhD student. I don't want to say nothing wrong about his work, but it was not his role, let's say, to prepare this let's say, this activity, and by a researcher who normally not working with the onboard software. In consequence, there was a number of failures, fortunately not critical. So we had a big issue with the cable routing. So as you imagine, this drum is rotating, the electronics is inside, but inside we have this switching of the RCE and the piston. So the cables was okay. Finally, the routing worked, but it was not, let's say, designed to work. It was not designed to work. By experimental adaptation of the, let's say, interior, we found the solution, but the cable routing wasn't a really issue. As you see during the, let's say, my mistake in the repetition of the container, we have opened one of the ceiling. This was actually the first experiment on the aircraft with the 10 kilogram of regolith, and the aircraft provider was really worried about this situation. So only our experiment was double sealed. So the drum was sealed and the whole container was sealed. And the rules was that if the regolith will appear besides the drum, there will be stop of the experiment. And such an issue, as you see, this circular element, this mechanics was designed a little bit before we knew that we need to have a double seal. So we somehow implemented the covers, but one of them during my manual operation of the replacement of the container, because after each day of the flight, we need to replace the container with the new regolith. So I wanted to speed up a little bit the process, and unfortunately, it was not a good solution. So during the second day, there was an issue with this sealing. Fortunately, there was no regolith. Let's say this regolith will not went outside. This is just to say that the procedures should be fulfilled, not to speed up. Of course, there is an issue because we have a very limiting time. We after the first day, we landing later because there was an accident on the flight. So we landing at 4 o'clock or 5. Normally, we should have 4 hours for replacement of the container. The provider asked us to shorten that period to 2.5 hours. And this was, okay, I don't want to say that this is operator failure. This was my failure, but there was such an issue. We had the issue with the software stopping in different moments. So we needed to restart the operation of the experiment a few times. We had an issue with the fuse, but fortunately not during the experiment. We had a serious issue with the battery. So we generally got the, let's say, acceptance of our big power bank inside the experiment. But when the, let's say, crew saw how big it is, they decided to exclude our power bank. So we found the solution. We had a small battery which we are able to operate, but there was a consequence that the operator need to switch on and switch off, let's say, camera after each sampling operation. So normally we would have the full video for 4 hours, but due to this reason, we have, let's say, 10 of videos just for experiment. And it is not an issue, but the operator has additional task, let's say, to do. Okay, and yeah, this is, I think, one of the lessons learned, that we have some issue with the main computer operating with Maxon driver, where we connected the end stop to the Maxon driver. So this I would change in the future. Okay, so I must say, or I want to say, that the cooperation with the flight provider and also system engineer from SpaceX and with Nova Space was really good. Means this was something which I like very much. They really support us. They really wanted to have an experiment with Regolith on plane. I also want to thank you, Military Wojskowy Instytut Medycyny Lotniczej, for preparation of the medical procedure to validate our operators for the parabolic flight. I want to say that the cooperation with ESA was really good, but I suggest every future coordinator to let's say, to arrange more operators. Means we asked for 2, but all other teams asked for more. And at the end of the story, they had much more operators for their much simpler experiment. So this is something which is important lesson learned, that is worth to ask for at least 1 more operator than is required for the flight. This is something which you know, which is related to the team, which is not from one institution. It is really worth to, let's say, to define the structure of the data which are logged during the experiments, and also how the open access rules are defined. So this was not required by ESA. This was actually required by the NCL. But it is worth to do that well in advance, let's say. From the, let's say, logistics point of view, I must say that the single house plus rented car for 8 persons for 2 weeks in Bordeaux is a good solution. However, I work also as a housekeeping person, so I had additional shift, let's say. From the funding perspective, this is my estimation of the cost. So I think, this I don't know. I think ESA paid around €1 per experiment. I tried to recover these numbers from, let's say, delegation, but without success. And the cost of the preparation of the experiment is around, in our case, around €130. Assuming that the RCE, of course, was developed as a separate contract. From the personal perspective, the flight was really tough for me. As a personal experience, I would not like to be an operator next time, but I know that, for example, Konrad really enjoyed. Okay, last but not least, if the proposal is not from the single institution, the rules related to the agreements, etc., is challenging. There must be one coordinator. So at the end of the story, if there are, for example, 4 institutions, or all institutions want to sign the agreement with ESA, but in all agreement, there must be the name of the one coordinator. In that case, I was a coordinator, but But this is the challenge issue. Okay, the future. So I hope we will at some times we will go to the moon. To go to the moon, I work a little bit on the definition of the mission. So what I really think is worth to realize in future is to measure the geotechnical properties of the soil. Of course, in the soil, where it means in the surface of the moon, but due to the fact that it is difficult to let's say to obtain large amount of the data, which is always useful. In my opinion, it is worth to move this regolith to the container and perform or repeat the experiment in the container just to have a chance to record from the site or in other way the soil movement. So this is few information. I am trying to finish the papers. This is something which we already started. Here is a nice paper related to this topic, which we done together with Tomasz Rybus and Arkadiusz Tkacz, but this is something which we are, let's say, plan for future to have a paper from that experiment, and that's all. Thank you. Tomek, I hope Tomek that I'm on time.
Okay, thank you, Karol, for a real exciting presentation. Especially the surroundings were unusual. And the first question I have to the audience outside: any queries from over there? Since I don't hear anything, I'll have a question to our medical team. Is Karol's future as an operator on the moon excluded? Magda, what do you think? Can you treat such symptoms that he suffered as something temporary, or he should be eliminated? What do you say?
I think that it is very common for the astronauts to develop this is called space sensitization syndrome. Just can't remember the word right now. But generally, no, he is not. It is very common to experience such things, and one can get used to it. Oh. Although it is possible that one does not get used to it eventually. So you cannot really tell right now.
So I can say that the scopolamine doesn't help me. But my colleague Konrad, who is also I see that he's attending, also had Konrad. You also had a scopolamine, but you didn't have any, let's say, problems during the flight. Am I right? Oh, maybe Konrad is muted.
Maybe he can't hear you.
But okay. So, but I had a problem after a few of parabolas. Means I think first 10 or maybe even 15 was fine. Then I had really problems with stomach. Let's say the flight operators helped me a little bit, but what was really helping for me was to look through the window outside. Means. And as you saw in the cabin, there is no window. And I'll come back to this. But not here, but okay, here. Okay, there is no window in the experimental area. So what I've done after each 5 parabola, I went to the let's say to the place where are the seats, and I just look through the window, and after 2 minutes I could come back.
As far as I can recall, there was a mission called Frame 2. They were going around the Earth like last year, and they were supposed to do some job, take some pictures, etc. For the whole day, on the first day, they were unable to do anything. It's just on the second day they started working. So just don't worry. Okay. It is all right. It doesn't exclude you from any space-related activities.
Okay. thank you.
And I've heard many people complaining, well, it's not complaining, just saying it was like this during the parabolic flight, that even the toughest guys, some guys or girls, sometimes, well, very frequently actually experienced the nausea, the vomiting, the claustrophobic probably feelings, but you can get used to it. And please keep in mind also that parabolic flight is not exactly the same as space, because it's acceleration, deceleration, acceleration, deceleration, and this gives you additional pain.
Thank you.
I have a question. Okay, you suffered a lot, but I suppose that you enjoyed a lot too, especially that you have a very unique set of data. I suppose that you didn't have time to analyze it fully right now, but do you have any first results and ideas how to improve your digger? No, it's not digger right now, but it used to be digger. Yes.
I don't have the first results. Actually, what I wanted to advertise here and in other, let's say, at other place, that I will try to find the PhD student, let's say, for the next period, and work with him on the data analysis. Yeah, the reason is simply that we are at the really end of the NCN project. We don't have the funds for the team and for the PhD students. I work a little bit on data side, but I also want to use it as a good, let's say, amount of data for the PhD students to have a nice work. I'm still a little wait.
Mm-hmm. Okay, maybe I wonder whether I'm stepping out too much, but I would request that you talk to Jarek Borek, who is very much into using additional tools that may help analyzing data in much more optimal time. So talk to him. Okay, and the last question I want to ask is, what are real advantages of having that experiment done? From what I saw, there was a difference in relative density. Anything else that you could tell was different?
No, the real difference is the power consumption. Means power consumption by the motor. And due to the fact that this power consumption impact on the temperature, there is an issue. Means, during the daytime, we have the temperature around 120 on the surface. Operation of the, let's say, motor increase that temperature, but typical limit for the motor is 150. So there is not big, let's say, not big margin. Having in mind all, let's say, acceptance and qualification margins from the ECSS, we are really, let's say, on the borderline. So knowing how the power consumption is reduced during the different gravity conditions, because it is not trivial, it is not by 6, not by 2, we don't know actually. We can say, let's say, or we can define much better the operation. Okay. The motor for the RCE was 6 times bigger than required, just due to this thing. That just to be sure that temperature of the coil will rise just by few degrees. If we would know how much power we will dissipate, we could have a little bit smaller motor, and let's say, let's reduce, for example, the mass or space actually inside the mass.
But judging what you just said and going back to that issue of the difference in relative density, it looks like the conditions on the Earth are much more severe than in the parabolic flight, right? I mean, you need more power, you need, so you would rather work with those limitations, right?
But on the back. Yeah, in case we would have, I don't know, 70-degree like on the satellite, right? I would not care because what is exactly what you said. We are far from the borderline in that case. We have the conditions more difficult than on the moon condition, and okay, we are in the conservative side, and that's all. But in this case, the situation is different. This is one point, of course. This is the technological point. Another point is, of course, that the let's say geotechnics is interesting anyway, you know, in the moon condition, because, for example, if you want to do foundation in the moon, you need to know the geotechnical parameters. So from that perspective, it is also important to understand how let's say, how the soil is moving. This is the reason why we have not only one experiment, but actually 3 experiments in our set. But
a total layman question here. Would it be ever possible to have some not fully space grade, but something approaching a vacuum chamber on board?
yeah, there was an experiment. There was one of the experiment, the third one. I don't remember which one from that list, but one of them, the experiment, they have the vacuum chamber inside. But of course, it was not like the vacuum chamber like we have. It was rather the rack with the size more or less like we have with the pump, with the turbomolecular pump, and they performed the experiment. I don't remember the let's say the full experimental setup, but I have the abstract list. So if you are interested, I can forward you the abstract lists of all experiments.
How did you contain an experiment like yours?
You know, the RCE is small, but the issue here, you know, this is okay. I forgot to mention about that on the slide. The mass of the RCE is just 2 kilograms, but the full mass of the experiment of our rack is 150. So we are using 140 kilograms just to have the mechanical device, mainly to reset the regulator. Means to reset the relative density, etc. of the regolith, to repeat in the repeatable conditions the experiment. So if you would like to add the vacuum to this condition, then we would exceed the maximum size. The maximum size for the NOVA space is 200 kilograms. So I'm not, but of course, yeah, maybe the solution is to have 2 racks and do something. Yeah. Okay, I have few ideas for the experiments in future, but not well defined right now.
I noticed that on one of visualization, the rack was mounted on the, I'm not sure if I'm heard, was mounted on a robotic arm. Could it be possible to make a simpler version of such an experiment, but in a way that it include also a small and light robotic arm that should perform this handling motion?
I don't know, maybe, but as I said, the robotic arm is a costly device. We didn't have at CBK PAN and the robotic arm ready to, let's say, to realize such a task. It could be possible, but still we have an issue with this regolith speed, because this must be, let's say, moved with in the different orientation with respect to the gravity. So
the whole resetting part would still need to be there, and on top of it,
Yeah.
the small and I see. Thank you.
okay.
Are there any other questions?
Okay, if no further question, I don't know, Edita, do you want to finish or I should?
Yes, I was in charge to finish it. Thank you very much, Karol, for extremely interesting. I have to recognize that I'm jealous. I would like to fly there, even if I know that my stomach is not good enough for that. Good luck for the future.
Okay.
And
Thank
let's hope to see it in the moon. We keep our fingers crossed. And I have one announcement. The seminar, the engineering seminar, will become the part of the CBK seminar. So it will take place on Thursday, usually. As in fact, the engineering part is our scientific discipline. So why we separate this? So, I hope to see you soon.
Okay.
Thank
you
you.
very much. Wysłał, ale teraz. Tak, ale mam. Czekaj. Zaraz zobaczę, czy wysłał, bo ja mam wrażenie, że jakby ja nawet coś patrzyłem, że tak powiem ostatnio na